In this video, we will be learning about significant figures and how to record measurements using the appropriate number of significant figures and counting significant figures. When we record measurements in the lab, there is some uncertainty to that measurement because we have to make estimates about how much we have of a substance. We have different pieces of glassware in the lab, and some are more precise than others. And so if you look at this beaker, you can see that the lines are 10 milliliters apart. And so we can see the liquid is between 20 and 30, and it's closer to the 30. And so we would have to estimate how many milliliters are in there, and we could record a measurement like 28 milliliters, or 29 milliliters, or 27 milliliters. And so somewhere in that range. All we know is that there's at least 20, and there's probably around 8. If we pour this liquid into a graduate cylinder that has markings every 1 milliliter apart, then we can see that the amount of liquid wasn't really like just 28, it was a little bit more than 28. And so we could record the measurement like 28.2, 28.3, somewhere in there. And then we could pour it into a burette, which has lines every 0.1 milliliters. And then we could see with even greater precision what the volume of that liquid was. So we need to be able to record our measurements in a way that reflects how precise our instrument was, so that other people know how well that number is actually known. The beaker is far less precise than the burette. And so a measurement made in a burette would have more significant figures to it than that of something recorded in a beaker. So we need to be able to convey to other people how precise our measurements were. And so the level of precision in your measurement should always reflect your instrument. So if we look at this ruler, we can see that that's a 2, and so that represents the ones place. And then this middle line here would represent 2.5 because there's 10 lines in between, and so half of 10 is 5, and so the halfway point is 2.5. So that's 2.6, 2.7, 2.8. And so it's just a tiny little bit beyond 2.8. So the 2 and the 8 are known digits. They are certain. Then we're allowed one estimated digit. So if it looks like it's halfway, you would write 2.85. If it's less than halfway, then you have to estimate with your eyeballs how far along is it. And so I estimated that it's a 1. And so I would record this measurement as 2.81. And so one estimated digit and then all of the certain digits. As far as tracking goes, we would count this as 3 significant figures. All of these digits are significant. All of the certain digits are significant, and that one estimated digit is significant. Go ahead and pause the video to record your measurement for this volume. You can assume that the unit is milliliters. Okay, so hopefully you are unpausing the video to double check your answer. So if we look at the main graduated cylinder, we can see that this line represents 20, this line represents 25, and there are 1, 2, 3, 4, 5 lines in between. And so this line must represent 21, and this line must represent 22. So that's 20, that's 21, that's 22. So the volume here is 21. Those are the known digits, the certain digits. And then we have to estimate. how far along it is. And so to me, it looks like it's barely past the halfway point between these two. We always want to read from the bottom of the meniscus. And so I would say halfway is like right there-ish. And so I think it's barely above the halfway point. And so I'm going to estimate 21.6. If you were close, if your estimated digit is like plus or minus 1, then you are in the right range. But your measurement should be recorded to the 10th place, because our last known digit is in the ones place. Not all numerical values are measured values. Some numerical values are exact values. Exact values are numbers that are either defined to be a certain quantity or numbers that are counted values. So for instance, defined quantities are like 1 dozen equals 12 counts of things. So like a dozen eggs, we know that a dozen eggs is 12 eggs. A dozen donuts is 12 donuts. That's an exact, by definition, 12 is equal to 1 dozen. Also, by definition, 1 week is 7 days. So that's defined to be that much. And so that's not measured, that's exact. Counted values are, for instance, 4 tires on a car, 2 hydrogen atoms on a water molecule, or the number of people in the room. And so those are counted values. When we're doing calculations, it's important to remember that exact values have unlimited number of significant figures. That means essentially infinity sig figs. So we won't count this as 1 sig fig and 2 sig figs, we will count it as infinity sig figs because it's an exact number. Now, I have mentioned that we need to be counting how many significant figures there are. But how do you know which digits are significant? So there's some vocabulary associated with this that you will encounter in the reading. But sometimes it's just easier to learn how to count without interfering with all those vocabulary words. In order to start counting, you have to find the leftmost digit that's between 1 and 9. So for instance, that one, these are your starting points. And then you count towards the right. And so we're going to have to count going that way. And then we have to figure out, where do we stop? We stop at the last digit if there's a decimal point. So if there's a decimal point anywhere in the number, anywhere at all, then you have to start counting all of the digits, starting here all the way to the right. Don't skip over any zeros or anything, just count all of them. So this number has 1, 2, 3, 4, 5, 6 sig figs. 1, 2, 3. I'll do it down here. We start counting there. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. I use SF for an abbreviation for sig figs. Now we have to find the leftmost digit between 1 and 9. That's my starting point. Then I count everything to the right. 1, 2, 3, 4. These zeros up in front are not significant. These are placeholder zeros. But you just have to remember that you start at the leftmost non-zero digit. So you start at the leftmost non-zero digit, then you count everything to the right. This same principle works even if the number is written in scientific notation. So in scientific notation, there is a decimal point. So you just find the leftmost non-zero digit and count everything to the right. 2, 3, 4. So that one has 4 sig figs. Now, if there is not a decimal point in the number, then you just have to stop at the rightmost non-zero digit. So you still start counting at the leftmost non-zero digit, and you still count to the right. It's just now you have to end at the leftmost non-zero digit. So 1, 2, 3. Now, this number is really, we would count it as 3 sig figs because that is the lowest number of sig figs it could have. These zeros are ambiguous. It's not clear the way this number is written whether that 0 is significant or if it's just a placeholder. So if this was a significant 0 at the end and we wanted this number to really have 4 significant digits, we should really be using scientific notation to help convey that which zeros, if any, are significant. If we do not write this number in scientific notation, then we can't count any of the zeros as significant. We have to count them all as placeholder zeros. So if you go through here, I say technically this number is ambiguous, and we should be writing the number in scientific notation to clarify if any of these zeros are significant or not. But since it's not written in scientific notation, we have to treat it as if none of the zeros are significant. And that's how we would end up with 3 sig figs. So let's practice counting sig figs. Go ahead and pause the video and work out on your notes which of these values are significant. When you're ready, go ahead and play the video and see if you were correct. Okay, let's go over this. So there is a decimal point right here. So we're going to find the leftmost non-zero digit and start counting everything to the right. 1, 2, 3. There is a decimal point in the number, so we find the leftmost non-zero digit, and we count everything to the right, which is nothing there, and so that's 1 sig fig. Oopsies. Then for this one, again, we find the leftmost non-zero digit, and we count everything to the right, and so that's 3 sig figs. There's no decimal point in this number, and so we can't treat that 0 as significant because it's not clear whether it is or not. And so we will count this as 3 significant figures, although if you said ambiguous, you can also say that. This one does clarify that that N0 is significant because it has a decimal point at the end of the number. And so you can count this as 4 significant digits. A lot of times in calculations, we have to round our number so they accurately reflects how many significant figures are in a calculated value after applying our significant figure rules, which we will talk about shortly. For now, we're just going to have to practice rounding to a given number of significant figures. So when you're trying to, for instance, round these numbers to 3 significant figures, we know we start counting at the leftmost non-zero digit. Then we are going to try to count out 3 sig figs, and then we would want to get rid of the 3 and beyond in this first example. That way we would end with 3 significant figures, according to this example. If this digit right after the digits that are retained is less than 5, then we're going to round down. When it rounds down, that becomes a 0. And we don't write the 0 afterwards, but that would be 2.44, and then that becomes a 0. And so that just drops off. So if that one digit past the digits are supposed to be retained is a 0, 1, 2, 3, or 4, round down. Then we'll skip over to if it's more than 5. If that digit right after the digits you're going to be retaining is more than 5, then you're going to be rounding up. So if your digit is a 6, 7, 8, or 9, then you're going to be rounding up. When that becomes rounded up, it's a 10. And so that 0 there is not written, but that 1 does add to that digit, and so then that would become 2.45. So we have to remember to carry the 1 there. Now, if this digit that we're rounding away is a 5, we're going to have to do something special, because statistically speaking, we need an equal probability of getting either rounding up or rounding down to be fair. And so you'll notice here, if we had a 1, 2, 3, or 4, we're going to be rounding down. If it's a 6, 7, 8, or 9, we're rounding up. And so this, if it is exactly 5, then sometimes we're going to be rounding up, and sometimes we're going to be rounding down. This is a little bit different than if you took Chem 3A at Fresno City College with me or several other instructors. In Chem 3A, we just simplified things and just said, hey, if it's 5, round up. But now we're in Chem 1A, and so we have to learn how to do things more properly. So the rule of thumb here is that your retained digit needs to become even. If it's already even, we don't want to change it. And so if it's already even, then you got to round down so that that last retained digit is even and it stays even. If this last retained digit is odd, then we're going to want to round up so that it becomes even. So if we rounded down, it would be 2.43, and then that's odd. And so we don't want that. We want to round up so that it becomes even. So once that rounds up, we carry the 1, and then it becomes a 4. And so then it's even. So if you don't want to get mixed up about whether you round up or down, you just have to remember that this last retained digit has to be even or become even in order for you to report your answer. All right, let's do some practice rounding. Go ahead and pause the video and work out this practice problem on your notes. When you're ready, unpause the video in order to double check your answers. All right, let's go over this. So this number is supposed to be rounded so that it has 3 significant figures. And so we have to count 1, 2, 3. That means we have to get rid of this 5. Since this is a 7, that's odd. That means I'm going to have to round up in order to make that an even number. And so that will become 7.8. 17.8. I think I misspoke. Next up, we have 9.66 to 2 sig figs. 1, 2 sig figs. We got to look at that 6. 6 is more than 5, so that's going to round up to 9.7. This one needs to be rounded so that it has 2 significant figures. 1, 2. And so I could write this as 150, or I could write this as 1.5 times 10 to the 1, 2. And this is the more proper way of writing it so that it has 2 sig figs clearly. And so this is the preferred method over this lack of decimal. This one's preferred. But I wouldn't mark that one wrong. It's just that 1.5 times 10 to the second is preferred because it's clearer that that 0 at the end is not significant. If you wrote 15, that is just wrong. 15 is way less than 151. So 15 is much less than 151. We have to make sure that that 1 stays in the 100th place. And the 5 stays in the tens place. And we do that by putting a placeholder 0 at the end of the number. Next up, we have this number that needs to be rounded to 3 significant figures. So that means we look at this 9. That 9 is going to need to be rounded up. That would become a 10, which would round up, which would round up. And so that 1 just keeps carrying over until we end up with 70.0. And all 3 of these zeros are significant, or these 2 zeros are significant, and so we do need to write them so that we convey that we have 3 significant figures. In this column, we are testing out your vocabulary for the different places in decimal notation, since that will be important when we are applying our addition rule for sig figs. So we have to first locate the 100th place in this number. The 2 is in the hundreds place. And so that means we look 1 digit past the hundreds place, which is a 5. And then we have to decide, do we round up or do we round down? The 2 is already even, and so if I round down, it will be even. So the 2, we have to make sure it's even. You could also write 1.52 and then turn this into scientific notation. 1, 2, 3, 4 times 10 to the 4th power. Next up, we have round 2.89 to the tens place. The tens place is here. And so this 9 is the one we look at. We're going to have to round up. And so that becomes a 10, which would carry over. And so essentially we need to have the number 2,900, but this 0 here needs to be significant, and this last 0 needs to be not significant. And so we're going to have to use scientific notation here because that's the only way to clarify that one 0 is significant and the other one is not. So we're going to have to write this in scientific notation so that we add clarity about which is significant and which is not. So that's 2.90 times 10 to the 1, 2, 3. I recognize that now it looks like there is no tens placed in this number. This is in scientific notation though. So 2.90, the 0 is in the tens place once this is expanded so that it's not written in scientific notation. This is just another way of writing 2,900. Now we will move on to the tenths place. The tenths place, that's a TH, and so that's after the decimal point. So that's that one. That's a 4, so we're going to round down to 3.4. Now we're going to round this one to the ones place. The ones place is this one. So we're going to have to look one digit past that in order to decide whether to round up or down. We're going to have to round up, and that's going to become a 10, and so then we would round up, carry the 1 over, and then we're just going to end up with 70. I can add a decimal point to clarify that this 0 is significant, or I could write in scientific notation, and I could write it as 7.0 times 10 to the 1 power. Either one is okay with me. Try to make your decimal points a little bold so that I don't have to go to the eye doctor to tell that they're there. And you don't write, actually, it's not like you don't have to, it's like you should not write any 0 or anything after the decimal point. The decimal point's just here to clarify that that 0 is significant.